Okay, so number 3. Okay, so we're looking at number 3 first. I did 1 and 2 this morning, so we'll start with 3. Okay, so when we're looking at the derivative graph, we have to recognize that what we see is not the actual picture of the graph, right? They're giving us slope information, which is not the same thing as location. So to help us remember what we're dealing with, let's label what we see in front of us. Anything that lands above the x-axis is going to be represented with a positive slope. The graph is actually, so even though there's rise and fall in all these regions, if you're looking at the graph, it's just, these are all going to show up as different variations of positive slope. So some steeper than others, but this is not the shape of the graph. The entire region here is all going to show a positive slope. Anything on the x-axis is going to be where slope is 0. And then anything below the x-axis is slope, negative slope. So if we want to create a slope sine line, we have our endpoints, which is from 0 to 9. And then you're going to fill in using x-intercepts. Because we want slope zeros to land on our slope sine line. So what are those going to be? Thomas, what do you think? Slope.
So wait, asking?
What critical points can we place onto our slope sine line?
2, 4, and 6.
Okay, 2, 4, and 6. And what are the slopes in each of those intervals?
0 to 2 is decreasing, 2 to 4 is increasing.
Good.
4 to 6 is decreasing, 6 to 9 increasing.
Good. So our graph is actually going to show this. It's going to show a relative min at 2, relative max at 4, relative min at 6. Okay, so the arrows are actually showing the picture of the graph. Now the second derivative sine line is where we can pull information about points of inflection. So points of inflection are going to be living in the peaks and valleys of the f prime graph. So what critical points do you think we can fit onto our second derivative sine line?
1, 3, 5, 7, and 8.
Good. And then the slope of the f prime is going to correspond with concavity. So anywhere that we see negative slope is going to correspond with concave down of the original graph. Anywhere that we see positive slope is going to correspond with concave up on the original graph. So I'm highlighting those parts there. Concave down of the original function. Concave up of original function. All right. So what's 0 to 1?
Concave down.
Yeah, and it keeps flip-flopping, right? Okay. So we have these two. This is all we care about. If we can get this, we can create f of x. We can create the graph. No longer do we need to look at this anymore. Okay. We can ignore our graph. We can just focus our attention on what we have in front of us here. So let's create a graph with these behaviors. Okay. The location doesn't matter as long as you can get the graph to be shaped like that. So we're going to do 2 drafts. First draft, I'm going to create a relative min at 2. When I think of relative min, I think of a lower value. So I'm going to just pick a point somewhere below the x-axis. That's just, it doesn't have to be, but it's just easy for me to find. 4, I'm expecting a relative max. So I'm going to pick a point relatively high. And then 6, a relative min. So relatively low as well. It doesn't matter if it's below or above the first one, it doesn't really matter. So I don't really care about curvature yet. I'm just going to create my shape. So using dotted line, it's not perfect, but all I want is the slope behavior. Okay. Two, three, four, five, 6, 7, 8, 9. Okay. Now I'm going to plot my points of inflection. So points of inflection are going to go along the path of the graph. So wherever my graph landed, I'm just going to pick off wherever I see, wherever the graph lands at 1, plot that point. Wherever the graph lands at 3, I'm going to plot that point. 5, plot that point. 7, and 8. And so what we're going to do is we're going to keep flipping the curvature from one point to the next. So from 0 to 1, now I'm not going to create a new path. I'm just going to go back. I'm just going to kind of update the curvature of my path. But remember with concavity, we're not going to be creating any more new path. It's just going to going back and just refining it. Okay, so from 0 to 1, I want to maintain this decreasing, but I want my graph to be decreasing, concave down. So give my graph a little bit of a concave down curve. From 1 to 3, concave up. 3 to 5, concave down. 5 to 7, concave up. 7 to 8, concave down. 8 to 9, concave up. But I'm just showing portions of concave down and concave up, right? I'm still maintaining that I'm not breaking any of my slope rules that I've already established. Good. So next step is graphing the second derivative function. So second derivative function, we're just going to build it from f double prime. We're not going to look at anything else. So now the difference is that the y-axis is not location, it's not slope, it's now concavity. So anything above is concave up, anything below is concave down, anything on the x-axis are our POIs. So go ahead and plot all of your points of inflection as x-intercepts. So I have 1, 3, 5, 7, and 8. So I have 5 POIs, right? And now we just have to match the location. Okay. Where do we want the graph to live between 0 and 1? But right. So, but it has to connect to that point, right? So we're going to make it rise. We're going to make it rise to that point. And then
stops at the next one.
Above, right?
Yes.
And then, but it's going to come back down, right? Okay.
Yeah, it's good back and forth, doesn't it?
Yeah, yeah, keys going back and forth.
Wait, what do we do with 9?
Oh, 9 is the ending point, so
Oh, so nothing?
nothing, yeah, it just stops. Good. All right, so try number 4 on your own. Exact same format. And I'll just see how you do. Okay, good. Give your graph. So build a graph just based off of that. So if you think it's a relative max, just pick a point high. If it looks like a relative min, pick a point below.
Yeah.
Okay, so these are not going to be x-intercepts.
Okay.
You want to follow the path of arrow, so what do you expect at the point?
Would it be like, I don't know, would it be a max? Oh,
It would be a max, yeah. So you want to just pick a point that is relatively high for your max. Do you need an eraser?
Yeah.
Doesn't matter what the point is, just pick a random point that's
Mhm.
high up there. Just
Like that.
and it's going to decrease from 5 to 7.
Oh, yeah.
Now, find where 2, 4, and 6 lands on your graph and highlight those points.
Okay.
Yeah. Good. And then between each of those points, you're just going to follow the curvature.
Oh yeah, shit. Dog.
That's okay. You just make it more bold.
I'll see it. Count the counts on all this. Just look different.
Concave down, concave down. Yeah, you're right. Yeah, you're right. It's not going to look a lot different. Okay, good. All right. So second derivative graph. Okay, so first thing you want to do is you have 2, 4, and 6, right? Create a graph with 2 and 4 sitting on x-axis.
Oh, that did backwards.
Well, I think you have the right track here, but here's what we want to do, right? So here's, you want this region to be concave up, you want this region to be concave down.
Oh, okay, so I did it backwards.
Yeah. So see if you can line up that information and create your graph. Okay, it doesn't have to loop back up. So it's just going to extend because we want the entire graph to be concave down. So the graph's just going to go up. It's not going to loop.
Oh.
Yeah, I think you have it looping back up, but it's not going to. It's just going to.
Oh yeah, so that's.
Yeah.
Okay.
Okay. Now, if there were more critical points, then we'll make it loop back up. But there's no critical points there, so it's just going to stretch away from the x-axis. Okay. All right, so see if you can do 1 and 2, and if you can get those done, then you should be comfortable with this topic.
Do I need to include the negatives?
Hmm?
Okay.
Oh, wait, say it again?
Do I need to include the negatives?
Yes, so you're going to extend all the way from -5 to 9.
So I include negative 4.0 something?
Oh, right. So make that go through -4.
Okay.
Yeah, that way it's easier, yeah.